department, I would like to welcome you to the live show. And as you can see, the entire seminar room is jam-packed by students, and some of them are still in their way. They will be coming after taking their examinations. And I hope students and you both, there will be enjoyment from the both end for this show. And I wish this show a grand success. Thank you so much. Over to Anirban. He will conduct the work.
Okay, so it's our great pleasure to have Professor David Spergel among us. First, we should be grateful to him because he has agreed to come online at 6:30 a.m. in the morning. So I want to have, I want him to hear from him. So some of you who still doesn't know about Professor Spergel, just let me introduce him. And it's a very difficult job to introduce him because you don't know what to say and what not to say. So Professor David Spergel was a professor in Princeton University. He has become emeritus professor in this year. Now he is also acting as a founding director of Center for Computational Astrophysics in New York. He has received lots of awards. So if I take the names of those awards, it will take a long time, but some of them is the Breakthrough Prize in Fundamental Physics in 2018, NASA Public Service Award, and he was also listed in Nature's top 10 people who matter in 2014. He has worked on several research fields from cosmic microwave background to early physics to exoplanet. So his research area spans over a lot of topics. And I don't want to take much time, but as I have worked with him, I just want to say that David is really a multitasker. So he can do many things at the same time. And what I always say that if I learned many things from somebody in a little time, that will be from Professor Spergel. So now I will welcome Professor Spergel. Please give him a big hand, and then we will start. Okay, David, now you can start your presentation.
Great, so it's terrific. How's the volume?
Yeah, volume is great. They can hear you.
Great. Terrific. So what I want to talk to you about this evening is mapping the universe. And what I want to do is begin by giving you my view of the current state of cosmology. And then I want to describe two efforts that I'm involved with to map the universe in different ways. One is by looking at the microwave background, and there I'm going to focus on some observation with the telescope and upcoming work with Simon's Observatory. And then I'm going to look at how we can survey large-scale structure of the universe and talk about some of the upcoming projects with a focus on NASA's W-FIRST mission, the mission that we hope to launch in 2020. And then I want to conclude by saying a bit about an ambitious program we've begun to apply machine learning for the goal of the construction of 3D map of the universe. So let me start with the current state of cosmology. What we've learned in the past 20 years is the universe is both remarkably simple and remarkably strange. Simple, in that with a model with 5 numbers, the age of the universe, the density of atoms, the density of matter, the lumpiness of the universe, how it varies with scale, and the overall amplitude of structure. We can fit all of our cosmological data. That's remarkable, that with only 5 numbers we can fit everything we see in the microwave background of large-scale structure and have what is generally a pretty good fit. We'll talk about some of the tensions as we go on. While this model is simple, what can be simpler than a universe with just a handful of numbers describing everything? It requires a lot of new physics. The atoms that make up us make up only 5% of the universe. There's 5 times as much dark matter as ordinary matter. We don't know what the dark matter is. It's probably some new subatomic particle that we haven't detected yet. And that's not even the strangest part. 75% or 70% consider the universe is in the form of dark energy. Energy associated with empty space. Our current best idea on that is vacuum energy. It could potentially be the signature of the breakdown of general relativity. So let me stop for those of you who haven't thought about cosmology and just repeat where we are. We think we understand a lot about the universe. On the other hand, we only know what makes up 5% of it. 95% of the universe is in a form that we've not yet detected. And I think this is an important challenge for you and others of your generation who pursue physics to figure out what 95% of the universe is. I think one of the things that happens when you're studying as a student, you get a sense that all the physics, all the science has been done, and your job is to learn that science and to be able to answer questions. That's not what research is like. There's an enormous amount we don't know. Other important ingredients that we don't know is how did the universe begin? What is the origin of fluctuations that grew to form galaxies? Basic and fundamental questions. We also don't know where the atoms that make us up come from. Our universe is baryon asymmetric. What we mean by that is we have many more protons and electrons than antiprotons and positrons. We do not understand the origin of this baryon asymmetry. All four of these things, dark matter, dark energy, the origin of the fluctuations, and baryogenesis, requires new physics beyond the standard model of physics. The physics we know cannot explain all four of these things, and all of them point towards new discoveries. What I have worked on primarily over the past 20 years are observations and analysis of the microwave background, the leftover heat from the Big Bang. And I believe you had a lecture already on the microwave background, but let me just remind you when we look at these plots, what you're seeing. What's plotted on the y-axis is power, the amplitude of fluctuations. What's plotted on the x-axis is where it bent, and you can look at this as basic. A scale associated with a given spherical harmonic is roughly 180 degrees divided by L. So the peak that first peak is telling us the characteristic size to the fluctuations is roughly a degree. And the oscillations you see in the spectrum, these so-called acoustic oscillations due to sound waves in the early universe, are all signatures of that fundamental scale. Now, there are a couple things you should take away from this plot. The first is the remarkably good agreement between different experiments making very sensitive, tiny measurements. So the amplitude of the signal is millions of degrees, microphone. And you can see 4 different experiments. NASA's WMAP experiment that I was involved with that launched in 2001, and its measurements of the fluctuations in blue. The Planck experiment, the European Space Agency mission that just reported its final results this year. The ground-based atomic cosmology telescope based in Chile. South Pole telescope based in the South Pole, all agree. We see consistent observational results. Perhaps even more remarkably, a theory, what we call the lambda cold dark matter theory, a model with dark matter and dark energy, is described by the curve. And you can see the curve goes through all of those points and captures all of those, fits that. And that's a model that was developed by a number of people, but led primarily by my colleague Jim Peebles, and work he did in the 60s and 70s and early 80s led to this is seen not only in temperature, but in the pattern of polarization. So when we look at the electromagnetic waves are polarized, and if they scatter off of something, I see polarization, and you can see a pattern of polarization. The pattern you see can be split into E modes and B modes, depending on the symmetry. A polarization pattern that is symmetric under mirror reflection is E-like, and those that is anti-symmetric is B-like. So we can also take the observations and analyze the E and the B modes. And if you look at this next figure, this shows again the Planck temperature measurements. In the top, same theory, fitting the Planck polarization measurements. In the middle, there's a temperature polarization correlation. And the polarization correlation in the lower left corner, and the lensing signal in the lower right corner. And again, it's the same model, we're not changing parameters, and you can see that it's fitting all of our data on the microwave sky. My summary of this, in many ways, was when we look at this data that Jim Peebles, who developed the theory, was right. And one of the pleasures I had earlier this month was I got to go to Stockholm, where I saw Jim win the Nobel Prize. And Jim was my professor. He taught me quantum mechanics and thermal physics, and was my colleague for 30 years. And it was a great pleasure to go to Stockholm to see the pomp and circumstance and see him win the Nobel Prize. Basically, for developing the theory that all of this rests on and what's been confirmed by these observations. So while we talk about everything working, there are some intriguing tensions that perhaps point to the need for modifications to the theory. When we estimate the expansion rate of the universe, the so-called Hubble constant, for the microwave background measurements, or for the measurement of a large-scale distribution of galaxies, we call the large-scale structure, the best fit value gets around 68 kilometers per second per megaparsec. When we measure the expansion of the universe and infer distances to galaxies using stars and supernova, we get a value that's somewhat large, about 73. Now, 68 and 73 aren't that far apart, so it's very important that we fully understand systematics and errors. This is a focus of a great deal of discussion right now. Some people think this discrepancy is pointing to new physics. Others feel, and I number myself among them, that this is likely a sign that we have subtle errors in our measurements. These numbers are quite close, and there are perhaps some subtle systematics in the way the observations are interpreted. When you have a situation like this, we need to do two things. One is develop new theoretical ideas that can perhaps explain this. The other is improve our observations, make independent observations, and confirm whether the value is 68 or 73 or perhaps something in the middle. And these measurements are indeed subtle. This plot shows the temperature fluctuations versus scale, again showing measurements now from WBAP, Planck, and more recent measurements from Chile in purple. And you should look at the two curves. One curve is the high value of the Hubble constant, the other curve is the low value, and you can see the differences are very subtle in measurements of temperature, which is one of the reasons we're interested in taking our polarization measurements. And if you look at the curve here, the differences become more pronounced, particularly look at the high multiples around L of 2000, 1800, 2000, where you can see the purple and the blue curves start to deviate from each other. The current error bars shown in purple are too big from our ground-based measurements to distinguish between these possibilities with our published data, and this is data published as of 2015. But what we've been doing over the past several years in Chile is making a more accurate map of the microwave sky. And with this more accurate map, we should be able to distinguish between the data. So in particular, we want to focus in on these regions here and look and see if which value is correct, to see if this basic model that we described of the Nobel Prize is describing the visible universe. So this is what we're doing in Chile. We're going to one of the driest places in the world, the Atacama Desert. There are parts of the Atacama Desert where it has not rained in recorded history. I've been to restaurants there that have open roofs because it doesn't rain. It's just always dry there. The geography is quite remarkable. You've got the cold current coming up from Chile, and that cold current dries it. That means it's very cold right along the coast, so air passing over the coast cools. When it then reaches the first mountain range near Antofagasta, it rains out, and very little rain gets to the desert. We're at a very high site, about 5,300 meters, right near the border with Argentina and Bolivia. And this is the telescope under construction. It's a 6-meter telescope that surveys the sky, and been doing this now for almost 15 years. We've been doing this with increasing sensitivity. Here's another picture of the telescope. And while the telescope is important, what's really important are the people. Because it's the people who do the science. Here's a picture of the science team at a recent meeting. Let's see, in the gray jacket, blue is Nicolia, who is in now. Many of the people on this team started as undergraduate or graduate students working on the project and have stayed with it, and eventually many of them have become faculty, and some of them now playing a leading role in driving the project. So right now we're working on the analysis. I can't yet report our new results. I can show some old maps to show you how things are improving. Here's a map that the Planck experiment took with the temperature. Here's our map, same region of the sky. You can see the improved resolution, the ability to see point sources. You can see the blue spots, which represent clusters of galaxies that we see through the Sinias Lodova today. You can see the increasing precision of the new data. We now have about 20,000 square degrees of sky. We're in the midst of doing our analyses and hope to be able to report out some new results, new measurements in the coming year. So, to give a sense of what we'll be able to do, this shows a power spectrum that we reported in a recent paper that came out in November. And you can see in the blue lines the measurements from Planck. And the blue lines, the curve you see rising to the right, this goes to much smaller scale as you've seen before, represents the contributions from dusty galaxies and those point sources you saw. With higher resolution, we're able to remove those, and we can then move towards the red curve, which you see below, and that lets us push to smaller angular scales and higher precision in both our measurements of temperature and polarization. And I've already talked about polarization, and let me just skip that, it's easier enough to show. So right now, we're trying to measure parameters from these maps. I can't report them. We're doing what's called blinded analysis. There's two of the people on our team, Steve Choi and Amelia Calvarese, and we are doing our analysis in a way in which we can see the answer, so that we're not persuaded by our desire to agree with one result or another. And it's only when we decide that the maps are done, that we've frozen the software, that everything is, that we'll open the box and look at the results. And we will do that sometime in the, we hope in January and hope to report results before the spring. So what can we do with measurements like this? Well, in addition to looking at the large scale, the early universe, when we look at the microwave background, we're looking at the universe 13.8 billion years ago. We also can learn about the intervening universe. As the picture on the right shows, as the microwave background's photons propagate from the early universe to us, moving forward in time, the fluctuations propagate through density fluctuations in the universe. And what we see is matter bending space, just as in general relativity. And on the left, just to remind you of the classic experiment of 100 years ago, classic observations of Eddington and others, when they observed during the sun's eclipse that when the sun's eclipsed, its position as seen by Earth, as background star shifting. That starlight for a background star got bent passing around the sun, and that was the classic observation of general relativity, showing that matter does indeed bend space. 100 years later, we're making use of the same effect by measuring how the gravitational lensing distorts and bends the microwave background fluctuations. It distorts E modes and P modes and introduces new patterns in the temperature fluctuations. So what we do, and this show reminds you that by distorting the positions, we change E modes into B modes. So what we do is we can take those observations and infer the distribution of mass. What this map is showing you is this is about 2,000 square degrees on the sky, so about 1/20th of the sky is shown in this particular map. This shows the large-scale distribution of mass inferred from the observations. So what you're seeing here is the effects of all the mass in the energy, more photons of high energy. As a result, clusters cast a shadow against the microwave sky. And we can look at that in our maps and look at how it depends on frequency. This is for observations of a distant cluster of galaxies. See the galaxies in the insert in the picture, and measured by Planck as a function of frequency. In the upper corner, you can see observations of the microwave background, what the background sky looks like, and then you can see as a function of frequency what the cluster does. At low frequencies, it casts a shadow. It actually blocks the light and scatters it up in energy. So we see a deficit of 30 to 150 gigahertz, and it scatters it to higher frequencies. So we see an excess at 300 gigahertz at the position of this cluster. So we can infer the total amount of hot gas in the cluster. What we've been doing with ACT data is making a map of the distribution of pressure across the whole sky. So this is a map of the large-scale distribution of all the hot gas. You can see in this map a number of bright white spots. We'll zoom in on some of their effects in a moment. Those are clusters of galaxies. You could also see some of the errors in the maps. You ought to be able to see a few bright lines that stretch across the map parallel to that. Some of that represents pickup from the ground. Remember, we're making measurements at the level of the microkelvin, so we have to put that out. And some of the features you see are due to, and then we infer the presence of clusters. And this plot here in the green shows all the new clusters of galaxies we've discovered. We're basically seeing all of the massive clusters in the visible universe, or now at the 15,000 square degrees we've analyzed in this particular analysis. So we'll look at about 40% of the visible shows rich clusters. whose mass is exceeding roughly 5 as a function of how feedback works and uses trace galaxies across the system. So that's where we are. What we're doing next is we're building a next generation experiment at the same site that will have roughly 10 times the sensitivity. We will first see light in about 2021 and start surveying in 2022. This Simons Observatory project is an international project. I think we have now about 250 scientists involved in this project. Spanning Europe, the US, to make up the team that's working on this project. This is funded by the Simons Foundation, which also supports my research at the Flatiron Institute. Right now, we're in the midst of constructing this project. This is where we are building it. This plot here shows the sky that we'll cover. We'll cover much of the visible sky from Chile. And the points shown in blue are hypothetical measurements compared to the current data. You can see that we're going to be able to push out to much smaller scales and see much higher sensitivities. We will have 5 times the angular resolution of the Planck experiment and roughly 10 times its sensitivity. So right now what we're doing is working on building these. We're building a series of 3 small aperture telescopes that are optimized to look at larger scales, to measure gravitational waves and look at E modes. And these are design pictures of a large aperture telescope, a 6-meter telescope that's designed to replace the App telescope you saw, have a much larger field of view, capable of working with 100,000 detectors, which will let us achieve the greatest sensitivity to date for measurements of the microwave sky. This is not just a PowerPoint project with just pretty pictures. This is something we're building right now. You can see pictures of detectors on the left. Detectors get placed inside an instrument that goes into the bolometers. Those are where it says LATR and SAT. Those are very large bolometers that pull the detectors down to the millikelvin, to the tens of millikelvin level, where they operate most efficiently. So they'll be operating at tens of millikelvin above absolute zero. You can see the team of assembling these, and these are getting incorporated into the large aperture telescope and way, making real progress in building the system. So now let me turn from the microwave background to observations of the large-scale structure. We want to learn about the intervening universe. And now I'm going to turn to a very different project that I'm involved with, called the NASA's W-FIRST mission. This project began in a sense in 2 different ways. One is through a process called the Decadal Survey. Every decade, the U.S. astronomy community identifies its top priorities for major projects for the coming decade. This is how we've identified projects like the Hubble telescope, the Chandra and Spitzer telescopes, and currently now working on the James Webb Space Telescope. Well, last decade we identified the W-FIRST telescope, the Wide Field Infrared Survey Telescope, as the top priority for the decade. Once money became available, we started working on this, and we plan to launch this in 2025. This telescope will survey the large-scale spectroscopic survey It will also do a large imaging survey. The distribution of mass. Planetary systems and beginning to characterize the planets. So this is the key technology for WFIRST. It is actually a repurposed spy satellite. This was a telescope that was originally developed to look down as part of a program that got sold by the U.S. government. We repurposed the telescope to look up and provided it with a wide field camera. This shows the area that the camera covers compared to the Hubble telescope and James Webb. It will cover each image roughly 100 times the area of Hubble at the same resolution. This will be very powerful for mapping the whole sky. Let me skip over some of the details and just give you a sense of how we can improve on cosmic parameters, measure the properties of dark energy, and give you a sense of how we'll survey the structure. So on the right, we're showing some very exciting things we'll have first, coming from the Euclid satellite, where we'll survey the large-scale distribution of galaxies when it launches in 2022. WFIRST will launch 3 to 4 years later. It will have 10 times the depth of the survey in terms of numbers of galaxies that it gets positions of, and it will be able to measure the large-scale distribution of galaxies across much of the observable universe. This ties in with our microwave background observation. The microwave background observation first show what the early universe looked like through the measurements of primordial fluctuations, then tells us about the integrated distribution of gas, pressure, electron distribution, and mass through its effects on the microwave sky. And then our galaxy observation gives us a three-dimensional picture of the large-scale distribution of the universe. We can then tie these together to look at how the universe forms and evolves. Now, I want to conclude by talking about the direction that our group is taking in thinking about how we want to analyze these observations. I hope I've given you a sense that an enormous amount of new exciting data are coming. I've only touched on a few of the experiments, WFIRST, Simon's observatory. There'll also be measurements of the European Euclid experiment, observations of a large-scale structure taken by the LSST telescope, which is a ground-based telescope in Chile, which will be mapping the sky. Already underway is a big survey called DESI, which is getting the positions and redshifts of millions of galaxies, letting us map out through those measurements the large-scale structure of the universe. And these observations, I think, are going to give us a tool for studying dark matter, dark energy, and the emergence of structure of the universe. And what we hope to develop are techniques for analyzing this data that go beyond just the 2-point statistic that corresponds to the power spectrum that I showed in that map. What we'd like to do is actually forward model the whole universe. I'm writing out an equation here that we're hoping to be able to solve, which is ask, what is the likelihood of the data? D here is the microwave background data. D prime is the large-scale structure data. What is the likelihood of the basic parameters of the universe given the data? And to do that, we need to be able to start with initial conditions. Start with the amplitude of all the fluctuations in the universe in 3 dimensions. Integrate forward. Predict where the galaxy should be. Predict the microwave background. Marginalize over uncertainties in the astrophysics. Marginalize over uncertainties in the observations. And basically be able to forward model from initial conditions forward to the observed universe. And then integrate over all possible amplitudes. And this is something that there's been some initial work done on, using simple approximations to the evolution of large-scale structure, but something that I think in the next 5 to 10 years, we should be able to properly do this and get a full history of the universe's evolution on large scales. So this will not be trivial. We want to model a volume of 100 billion cubic megaparsecs with a resolution of a few megaparsecs. This requires integrating over 1 billion variables when we evaluate the likelihood. And for each integration, we need to evaluate the evolution from the initial conditions of the observed galaxy distributions. We need to marginalize over the astrophysics. We need to project into the observational plane, include systematic effects. And the trick to this will be developing new tools. The focus of some of the efforts at the Flatiron Institute is to make use of machine learning as a tool to enable fast analytical mapping from initial conditions to today, ways of projecting from the dark matter to galaxies of gas, and ways in which we can marginalize over the baryon physics. I'm showing pictures of 2 of the scientists leading the effort, Shirley Ho, who's a group leader at the Flatiron Institute, and Francesco Venezuela Navarro, who is one of the researchers who's playing a leading role in developing a lot of the software we're using for this. So how will we do this with machine learning? Well, the first step is to learn how to forward model the dark matter evolution. So what we do is we begin by taking analytical predictions of how to go from initial conditions to the large-scale distribution of matter. We then take n-body simulations, and those n-body simulations will take millions of computer hours to run. We'll watch them evolve from initial conditions to the answer, to a physical state. And then we look at the difference between the analytical predictions and the numerical calculation. We then train a neural net. Analytics capture the largest scale as well. What we need to learn is local, so we're training a UNet using a conformal neural net to learn how to make these predictions. And the machine learning has been quite successful. To give you a sense of how much it improved, on the other side, you now see the displacements, the area of displacement done with machine learning, and you notice the plot is almost entirely blue. The errors are typically below half a megaparsec. We're getting an order of magnitude improvement in how well we can predict things analytically. And while the nice features of a neural net, it's an analytical map, so we can differentiate it. We can use that to use techniques to improve our fix. And importantly, this runs much faster than doing our numerical simulations, roughly 60 million times faster than running a full n-body simulation. Improvement in speed makes it feasible to survey over initial conditions and try to find what initial conditions predict a large-scale structure. The plots show the differences between the benchmark model and the predictions from machine learning, and you can see that if you look at things like the transfer function or the power spectrum, the truth is shown in green, how well we're doing in matching the data in terms of fairly small scales. So this gives us the distribution of dark matter. Our next step is predicting where the galaxies are, where the hot gas is. For that, what we do is we take big hydro simulations. What's shown here is the illustrious TMG simulations. These take hundreds of millions of computer hours, CPU hours to compute on some of the world's largest machines, and they predict where the hot gas is, where the galaxy should be. We then train the neural net on learning how to assign hot gas and galaxies to the dark matter distribution. This lets us learn from the simulations where the galaxies are, and use that prediction. We'll use that prediction to compare to our large-scale structure observations. So shown here in this movie is the evolution of the gas, the large-scale structure. Here you see the hot gas emerge. And you see explosions from AGNs driving the hot Church simulations. There are, of course, uncertainties in the simulations, and what we plan to do is run these simulations with different sets of parameters, train on the range of parameters. This lets us marginalize over the uncertainties in the parameters. And which underlying astrophysics best fits the large-scale distribution of galaxies from these surveys, enable us to get the maximum value out of these surveys. You can see the hot gas and forming as the simulation moves forward. So what we will do is use supervised learning to learn how to go from the distribution of dark matter to the distribution of galaxies. What we're effectively doing is learning a function that predicts the density distribution of the galaxy field, of the density distribution field of the matter, the gradients and the shears and the potential. It will let us train our neural net. We've just completed a set of 43,000 full and body simulations surveying over 7,000 cosmologies. These simulations mean we now have predictions for over 8 trillion particles. These simulations were very time consuming. They took over 35 million CPU hours. And we generated a petabyte of data. And this large data set is what we're using to train our neural nets. We're also running a series of hydrodynamic simulations. So we're running air. Bring this forward again. We don't know what the dark matter is, we don't know what the dark energy is. We have these big open questions we want to address. We're in the fortunate position that we've had to look forward to the next decade. There's tremendous advances that's happening in observations. I talked about the next generation microwave background experiments and where we are with, we had a number of big surveys taking place in much of the sky. I said a bit about the W-FIRST mission, but it's only one of the big surveys. And I concluded by talking about some of the new approaches that are enabled by machine learning. I see some real opportunities to go beyond the statistical techniques that we've used in the past years and emulate what happens in the simulations and do a full nonlinear evolution effectively that lets us reconstruct the formation history of a whole universe. And that ambitious goal is something I think we can realize in the coming decade. And I hope this talk is giving you a sense of the tremendous intellectual opportunities that I see in cosmology in the coming years. We have big questions, the data is rapidly improving, and there are important theoretical challenge, both fundamental physics, thinking about questions of the nature of dark matter, and challenges of computational physics, trying to carry out the simulations needed to reproduce the world's spectroscopy. So thank you for listening. Let me stop here and try to take some questions. Thank you.
Okay, thank you very much, David, for giving us a wonderful talk and talking about the future experiments. And now I'll take some questions from you. So just raise your hand. Okay.
আমি তোমায় বলছি তুমি উত্তর করে দাও এই ডার্ক ম্যাটার কেন লুমিনাস নয় বিকজ আমরা জানি ফোটন ইলেক্ট্রোম্যাগনেটিক ইন্টারঅ্যাকশন করে তাহলে কি ডার্ক ম্যাটার ইলেক্ট্রোম্যাগনেটিক ইন্টারঅ্যাকশন করে না
Okay. So one student named is Rick, and he's asking why dark matter doesn't interact with electromagnetic wave.
Well, why? So we don't know what dark matter is. All we can do is observe its properties. If dark matter interacted with electromagnetic waves, we would have seen its effect. So we can look in a number of different ways. We can look, say, for example, at a distant quasar and ask, is quasar light affected by the dark matter along the line of sight? Do quasars that have more dark matter in front of them, do they look dimmer than quasars that have no dark matter in front of them, less? And we don't see any variation. So that's one way in which we can tell dark matter doesn't interact with light. Another is experimental. If dark matter is some new subatomic particle, then because the dark matter fills our galaxy, there's 1 million dark matter particles streaming through our bodies every second, streaming through our experiments. If the dark matter had electromagnetic interactions, it would be interacting with the electrons and nuclei in our experiments, and we don't see it. So what we have at the moment are constraints on the dark matter interactions, either through the electromagnetic interaction, the strong interaction, or the weak interaction, with ordinary matter. The current best experiments come from underground experiments using liquid xenon that can constrain the interaction, cross sections of the dark matter to be quickly about 10 to the minus 12 times weaker than the interaction of neutrons with ordinary matter. So we know whatever the dark matter is, it interacts extremely weakly, which is why we've nicknamed many of the candidates for the dark matter particles WIMPs, or weakly interacting massive particles.
Thanks. Any other question? Okay. Any?
Actually, my question is, how did we come to know about the existence of dark matter? Was it, did it just popped out of some calculations or some experimental results? And if we don't know anything about it, why is it so important that we are investing so much funding or we are investing so much of knowledge behind it?
Okay. So David can answer it well.
Yeah. So the first observations of dark matter, the first inference of dark matter, goes back to Fritz Zwicky in the 1930s. Zwicky was observing the motions of galaxies in clusters, and he realized in order for those galaxies to be gravitationally found, there had to be much more matter in the galaxy, in the clusters that he could observe in stars. So that provided almost the first observational evidence for it over 70 years ago. Subsequent work in the 70s, led by Vera Rubin and Alfred Bosma, trace the distribution of, infer the distribution of matter in individual galaxies by looking at motion of gas and stars in circular orbits. What they saw was, take a galaxy like our own, most of the starlight is interior to the orbit of the sun around the center of the galaxy. But when we infer the distribution of matter, what we see is that the matter distribution goes much further out, and that the matter distribution contain more than 10 times the mass we see in the stars. So that we can, we see this distribution in galaxies like our own, and subsequent to that, when we try to understand our cosmological model, try to understand the distribution of large-scale structure, we realize that the same dark matter that we needed to explain the properties of individual galaxies, we also needed to explain cosmology. So from this, we learned that there's dark matter, and it's something that interacts gravitationally. And we haven't figured out how else it interacts. We're looking for it. Why is this worth doing? Well, some level, it's fundamental curiosity. There's something in our universe that's 5 times more common than atoms, and we don't know what it is. We want to figure out what's out there. And I think what drives us is, as physicists, doing a fundamental work is a desire to understand. There's something new to discover. If we can figure out what this is, this will tell us much, hopefully a lot about the basic properties of the universe. Why is this worth investing? Well, there's a couple of answers to that. One is a poetic one. We have a drive to understand the universe around us. This is something that humans have been doing since we evolved our intelligence, and we want to. This is an important part of missing piece of our understanding. And then there's the more practical one, which is advances in physics enable advances in technology. When Maxwell developed his theory of electromagnetism, he didn't imagine that it would enable technologies that would let me sit at my kitchen table in New Jersey and talk to you in India. And so whether you look at things like how studying the detailed properties of nuclei led to magnetic resonance imaging, we often develop physics that lets us develop new technologies. But also, in doing these searches, we tend to develop technologies along the way that's quite useful. So it was physicists working at CERN who developed the World Wide Web, right? And that has had an enormous impact. They did that not to develop a technology to make money, but rather to develop a technology that enabled them to communicate better among scientists. And that communication has led to the internet, which has had enormous impact on our society.
We'll take another question. So,
hello sir, I'm Raj. I want to say about that, we all know that the cause of accelerating expansion of universe as dark energy is the main reason. And another reason is of such case when gravitational wave emerges between the collapse of black hole or neutron stars. I mean to say that gravitational wave produces because of collapse of black holes or neutron stars. So my question is basically, have you had any chance to interact with gravitational wave or with dark energy? My question is basically.
Sorry, I couldn't hear the question.
My question is, have there any chance the interaction between dark energy and gravitational wave energy?
he is basically asking if there is any chance of interaction between gravitational wave with the dark energy.
That's a very interesting question, which is, as the gravitational waves propagate, are they affected by dark energy, or are they affected by space along the line of sight? And this is something that we did not know the answer to until very recently, when we saw the detection of gravitational waves with LIGO, particularly from neutrons, star neutrons. And what we saw was that the amplitude of the gravitational wave signal was consistent with no interactions along the line of sight. And this is something that I explored with working with one of my graduate students at the time, Chris Pardo, and also worked with Maya Fishbach in Chicago. So what we did was we compared the energy seen in LIGO with the energy predicted, and pointed out that if the gravitational waves interacted with the dark energy, if they effectively had lost energy as they propagated, the signal we see would be much weaker. So we were able to constrain the strength of interactions between gravitational waves and dark energy. So far we've seen nothing. But it's exactly the kind of question that you just asked, is the kind of thing we like to think about when we want to try to figure out new ways of detecting the nature of dark energy.
Thanks.
ট্রান্সলেট করে
আচ্ছা আচ্ছা
আমাদের গ্যালাক্সি তো স্যার পুরো ম্যাটার দিয়ে তৈরি, এমন কি কোনো গ্যালাক্সি থাকতে পারে যেটা অ্যান্টি ম্যাটার দিয়ে তৈরি, সেটাকে ডিটেক্ট করা যাবে কীভাবে? ব্যারিয়ার অ্যাসিমেট্রি তাহলে ওটা ক্যান্সেল হতে পারে। নামটা সমীর।
Okay, so Somir is asking that our galaxy is made of very unique matter. Is there any possibility that there could be another galaxy which could be made of antimatter, or if we can detect those aspects of a galaxy made of antimatter?
Yeah, so this idea that part of the universe might be dominated by baryons and other parts dominated by antibaryons, like matter and antimatter, was explored a lot in the 1970s. People thought maybe there were regions that were dominated by protons and regions dominated by antiprotons. If that were true, there would be a boundary region between this region dominated by protons, this by antiprotons. There would be a region in between where the two would collide. Think about what that would predict in the early universe. Well, the early universe was very hot and very dense. You'd have a dense fluid of protons, a dense fluid of antiprotons. There'd be a boundary layer between them where the protons and antiprotons would be annihilated, dumping in enormous amounts of energy, producing lots of gamma rays when the protons and antiprotons collide. When we look at the microwave background, we're primarily looking at the universe about 300,000 years after the Big Bang, when the temperature was about 3,000 degrees Kelvin. Well, that's hot. That's not hot compared to the X-ray energies. So what that would have done was dump an enormous amount of energies into the microwave background. And the fact that we see the patterns that we do see lets us rule out the possibility that there are parts of the universe that are dominated by baryons and parts dominated by antibaryons. Because we would have seen the boundary region for microwave sky. And there was earlier work, even before people were able to look at the microwave background fluctuations, where people looked for the gamma rays that would be produced at the boundaries. And the lack of detection ruled out this hypothesis.
So my name is Shoykot, and my question is that is the Big Bang conclusively and theoretically established as the origin of the universe? If it's not, then what is what exactly prohibits it from being totally established as the conclusive theory to the origin of the universe?
So what we know is the universe is expanding. You can see galaxies moving away from us. We look back in time, we see it was hotter and denser. We look at the microwave background, we can see that it was hotter and denser early on. So what we know is the universe is expanding. So running time backwards, you go back in time, the universe must be hotter, denser, denser. We can extrapolate back in time to a few, to within nanoseconds of the Big Bang and feel we have a reasonable understanding of physics. But the further back we go, our knowledge of physics starts to break down. As we get back towards the initial singularity, the point at which the density and temperature diverge, our knowledge of physics breaks down. We do not have a successful theory of quantum gravity, a theory that ties together general relativity and quantum mechanics, a theory that unifies all the forces of nature. So without that successful theory, we don't have the tools to predict further back in time. So we actually don't know how the universe begins. Right now, there are sort of three competing ideas that people explore. One's an idea that says that the universe began in a hot Big Bang and there was nothing before the Big Bang. This is an idea that Stephen Hawking, among others, have promoted the idea that asking what was before the Big Bang is like asking what's north of the North Pole. It's not a sensible answer when you talk about the geometry of space-time beginning at that point. A second set of theorists explore the idea that the universe is actually infinite in time and goes through a series of collapses, bounces, and oscillates back and forth, and we're now in an expanding phase, but that eventually we will enter a collapsing phase. And third set of theorists explore the possibility that we're living the universe is a quantum field, and that this is one of many possible universes that are and enacted during the work to explore these speculations.
Sir, my name is Ankan, and my question to you is that during the Big Bang, the inflation period, there was both matter and antimatter. So the interaction of the matter and the antimatter during that period could be a result that some of the matter has been lost. It is proven, or it's just an hypothesis?
Well, we think that, as you said, the early universe was very hot and very dense. It was filled with both matter and antimatter. The fact that the universe today is dominated by matter suggests that there's a slight excess of matter over antimatter. For every 10 to the 9 antiprotons, there was 10 to the 9 plus 1 protons. There was this slight asymmetry between matter and antimatter. Now, we're not sure where that asymmetry comes from. A very plausible idea is that asymmetry actually comes from the neutrino sector. And recent experimental data showing differences in behavior between neutrinos and antineutrinos might be pointing towards an explanation of the origin of those fluctuations.
So myself, Olive Dash. My question is.
Excuse me? Hi.
So my question is, as dark matter doesn't interact with anything else, so how can we detect dark matter? Is there anything way out to detect the dark matter?
Well, all we can say is dark matter interacts weakly with ordinary matter. And what we hope is that there is some weak interaction, and that we can detect those weak interactions in the experiments. So we aim to make the experiments more and more sensitive so we can make those detections. So I'm going to have to go soon here, so I should probably just take one last question.
Yeah, last one question.
Both of you. Will it be okay if I give you? Okay, last one is the Okay.
So he's asking that our universe is floating on the superfluid. Is it true? Or can dark matter be considered as a superfluid, if there is any possibility?
Could be considered what, sorry?
If dark matter could be considered as a superfluid.
As the superfluid. We don't know. There's been some interesting work suggesting, exploring the idea that the dark matter could be something that behaves superfluid, something like that. So, with light dark matter, at this point, we don't know what the dark matter is. So people explore a pretty wide range of ideas and try to find ways of testing it.
Okay, so now we will conclude the session, but I have a request. Let's say not a question. I have a request to you. So, would you like to give a message to these young students who wants to take cosmology as their research career in future, and what will be your message to them?
I think this is a very exciting time to be a cosmologist. We have profound theoretical questions to answer: the nature of dark matter, dark energy, the origin of fluctuations, and we have the good fortune to have lots of data coming in the coming years that might let us address this question. So I think it's a terrific time to go into the field, whether you're interested in observations, theoretical work, numerical simulation. There's going to be a lot of exciting opportunities.
Okay, thank you. Let's give David a big hand. Thank you very much, David, and thanks for coming.
Enjoy the rest of your meeting. Thank you.
Yeah, see you. Bye-bye.